Good afternoon, everybody. We are now starting the next section on monitoring drinking water quality with ICP-MS. I would like to introduce our speakers. Ms. TRAN. She is a head of atomic microscopy at Analytik-Jena Far East, as shown in this notebook. So she has worked in ICP-MS and AAS for 30 years. Yeah. So I'm sure that you will get a lot of knowledge from her. Ladies and gentlemen, please join me to welcome Ms. TRAN.
Good afternoon, ladies and gentlemen. I'm very grateful for you to spend your lunchtime sitting here listening to me. Thank you very much. I will try to make this section as interesting as possible to stop anyone falling to sleep. If you want to, you can, but just don't snore, all right? Okay. I'm talking about how to monitor drinking water with the ICP-MS, right? As we know that water on the Earth's surface, 3/4 of the surface is covered by water. And we need water every day for our life. And also, because the cell in our body, we need water for the body to function. So that means that we need to drink water every day. So the quality, safe drinking water is very important to maintain our healthy life. Where are the drinking water sourced from? So drinking water mainly come from groundwater, in the ground, or from the springs, which is, you hear the spring water. When you buy the bottled water, they say spring water from the springs. Or raining, or in the cold climate, they come from snows or glacier. And also, we heard the term surface water. On the surface, it means that come from maybe the lake, rivers, streams, and also some drinking water come from seawater. Maybe in the area they can't access to a clean, fresh water. That they need to remove the sodium in the seawater, the process called desalination. So that's called desalination seawater. Or from the water supply network. Right. So since drinking water is so important to our health, so different country authority, they set out guidelines to make sure that the elemental contaminants is within a certain limit. If outside the limit, they will affecting, if you drink the water contaminated, they will affect our health, right? Of course, World Health Organization, WHO, they set out guidelines. So guideline means that I recommend, this is the specification. Doesn't mean that you must follow it, but most of the countries, they all follow the WHO, and they modify for their country's specific conditions. And also, European Commission in Europe, they had the EC 9883 directive. And in America, the US EPA, they set up the guideline, and also they have the so-called Safe Water Act, Safe Drinking Water Act. Of course, you can see in your country, Thailand, right? So you can see different elements and different guidelines. So some are similar to the WHO, some are slightly different. As I say, they all follow the WHO guideline and they modify to their country's conditions. Out of this, only the European and the American, the US, they legally set the requirement for the drinking water. Other countries, they just say this is a guideline, you meet it or you don't meet it, doesn't matter. They don't really, not enforce it. But European and USA. You must, if this is drinking water from a drinking water plant, then you must meet this guideline. So it is important to monitor the elemental impurity in the drinking water. Right? So to measure the elemental impurity, there are different analytical techniques. Right? Graphite furnace, atomic absorption, or ICP-OES, inductively coupled plasma optical emission spectrometer, or ICP-MS, inductively coupled plasma mass spectrometer. So all these techniques can be used to determine the trace metals in drinking water. Now we all know that graphite furnace is a single element technique, so you need to measure one element at a time, and it takes 2 minutes per sample and at ppb level. ICP-OES, the test limit is about sub-ppb level, while the ICP-MS is sub-ppt level. Now, we just briefly look at the detection limit for ICP-MS. You can see they all sub-ppt level. So the milligram per liter is ppb, but they all 0.00 something, means like 0.02 means 2 ppt. And because they are at ppt level, so it is very, very important to use ICP-MS to monitor the quality of the elemental impurity in drinking water by ICP-MS because of such a low detection level. Okay, so what is the ICP-MS instrument, right? So you can see over there, there's an instrument that's called ICP-MS, right? May I ask, for those of you sit here, anyone have experience with operating ICP-MS? So familiar, right? Okay. So I will start from basic, right? What is ICP-MS? So firstly, we go back to very basic first year university. What's the structure of an atom? The structure of atom consists of nucleus in the middle, and then there's a photon and neutron, and then outside orbit is the electron running around. So that's the structure of the atoms. The total number of proton and the neutron, and it's called the atomic mass. And why it's called ICP-MS? Because we are dealing with the mass. So we are talking about atomic mass. Right. So you look at the periodic table, there are many elements. So for example, if I choose nickel, and then I obtain the nickel mass spectrum, you can see there are 5 different peaks. Because nickel has 5 different stable isotopes. So each of the signal representing an isotope. So what it means is nickel has atomic mass of 58, 60, 61, 62, and 64. Now you might wondering why the peak? Some are taller, some are shorter, different intensity, different counts. That is because the natural abundance percentage, natural abundance is different. The 58 had a very high signal because it has 61% abundance, comparing to 64 only 0.93. So when we are trying to measure the counts of elements and isotope, we normally choose the most abundant isotope for the measurement. Only if that isotope is interfered by something else, then we might choose the second one. So most of the time, the first most abundant isotope. Right. So the component of ICP-MS is very simple. There are 5 different components. Firstly, of course, most of the time the sample is liquid form. Some sample could be solid, but it needs to use the different accessories. So the liquid form of the sample will go to a sample reduction system, and then to the plasma. Now, what is a plasma? The ICP plasma is made of, it's generated by argon. So it's basically argon plasma. Right. The plasma is a 4 matter or 4 state of matters. You know the state of matter? Liquid, solid, gas, and then plasma. Plasma are the 4 state of matters. And because it is an argon plasma, it's generated by inductively coiled, inductively and then coupled form of plasma. So the plasma is very, very hot. between 7,000 to 10,000 degrees. Because it's so hot, you learn from first year basic, right? Wednesday, room temperature, and then absorb a lot of energy, jump up, and then emit atomization, ionization. So lots of ion generated to the plasma. And then pass on to interface. The interface consists of two cones. So it's called the cone interface. Sample cone, schema cone, and then the sample has to go through the cones, through the vacuum chamber, and then turn 90 degrees to the optics. The optic is to guide the path of the ion into the protocol, or called the mass analyzer. And then measure the count by the detector. So we have the plasma system, we have the interface system, and then the optics, then the mass analyzer, the protocol, and then the detector. So these 5 components form the basic component of ICP-MS. So it's very simple. ICP-MS have 5 components. Right. So as I say, the sample has to be in liquid form, and then it pumped to the peristaltic pump, which I'll show you later on in the instrument, and then to the nebulizer. Right, so the sample will come to the pump. I don't know whether you can see, nebulizer, and then this is called the spray chamber. The spray chamber function of the spray chamber is to minimize all the big droplets. Only the 5 droplets will be able to reach the torch, the plasma here. Sorry. Okay. So when the sample going to the plasma is so hot, so from liquid phase and then vaporize to solid, and then atomize from gas to atom, and then ionize, become iron. So the iron is the ion we want. So we need to count how many iron in the samples. And then to tell the plasma there's some air entrenchment, so there's slightly form some oxide, and to tell the plasma. Right. So this simulation, how the sample going to the torch and then to the plasma. After that, it will go to the cones. See the 2 cones, the sample cone, and then the schema cone. So the sample going through like this. Now, why between the 2 cones is under vacuum? It's vacuum. Why? Because it's vacuum. Because if you want the ion beam coming through, you must under vacuum. Without vacuum, the ion beam just drop out. I mean, your sample just drop out. So it's under vacuum and then going through. And after it pass the cone, and then it will go to the optics, right? So while we are here, I talk about the interferences, right? So remember, we are talking about mass here, mass, right? So the plasma is argon. So the major mass in the argon is argon 40, right? Remember we learned argon 40. So 40 is your major interferences. Argon 40. There's an element called calcium, Ca, the same isotope 40. So what it means that if I want to measure calcium, I will be interfered by argon. But don't worry, calcium have other isotopes. So instead of using 40, I can use 42, 46, 44, etc. So the same as selenium 80. And you know argon dimer, so argon 40, 40, and there will be argon 80. So if I want to measure selenium 80, I can't because I will be interfered by argon dimer 80. But don't worry, selenium have different isotopes. So there's 78, there's 82, etc. So I can use 78. But even 78, they're interfered by argon 40 and argon 38. But because the percentage abundance of 38 is much smaller, so I can measure selenium 78. All right. But what happens if the element only have one isotope, like arsenic? Arsenic 75 only have one isotope. And arsenic 75, argon 40, chlorine 35. If my sample is digest in HCl, then I would experience these interferences. Then what should I do? Right? So that means I need to try to look for a way how to minimize, remove my interferences. Okay? So to do this, we use so-called collision reaction cells, right? So in a very, very small confined area, we pump in helium as a collision gas or hydrogen as a reaction gas. Right. Okay, so this is an example. I click everything up here, alright. So arsenic 75, it could be interfered by calcium 40, chlorine 35, right? Now when I pump in helium gas, right, and then it will create collision. Now because arsenic is a single atom, while arsenic chloride is the molecule, because two means molecule, right? So during the collision process, because argon chloride is bigger, so during the collision process, it loses its kinetic energy. It loses kinetic energy means that it losing energy, so it will slowly remove from the system. So only the 75, the single atom isotope arsenic, be able to go through the system into my quadrupole. So this way of removing interference is called KED, kinetic energy discrimination. All right. So when you hear people talk about KED, I minimize, I remove my interference using KED is this sort of process. All right. So using this, then I remove all my interferences. After my interference will be all removed, then it will go turn 90 degrees into the so-called optics. So optic is basically focus all the positive charge ion, let it go into the quadrupole. So all the photon, all the neutron will disappear. And because this way, so all my other interests can be able to concentrate and go into my quadrupole. So quadrupole, as its name says, quad means 4, so means the 4 rods. So opposite side is linked to RF, the other opposite side is linked to DC. So this way of alternating, be able to each time only one M/Z go through the system. But because it goes through so fast, we feel like it is a simultaneous way. But in fact, it's one M/Z go past at a time. So basically, a sequential way of going through. But it's so fast, so it feels like it's a simultaneous. Okay, after it goes through, so this is the simulation, how it goes to the quad. After it goes to the quad, I need to count how many ion count, right? So to count the ion, I need to have a detector system. So the ion or photon will band onto this so-called different dynode, a row of dynode, DDEM, discrete dynode, electron multiplier. So it will band to the dynode and then multiply, and then I can count. And so that's why the sensitivity becomes how many counts per second. Right. So what can ICP-MS can be measured for? I can measure using ICP-MS to quantitative measurement. Or I can even use it for semi-quantitative. Semi-quant means that if I want to measure 10 elements, I only need less than 10 elements standard. I don't need 10. That's called semi-quant. Or I can measure isotope ratio. Isotope ratio means that I can measure the different ratio of the isotope or element, or different ratio of isotope between the different elements. So the isotope ratio is for fingerprinting, to make, like if I want to measure to know this rock, how old this rock is, then I can measure the ratio of between uranium and thorium, measure the ratio of the isotope, then I know, oh, this rock 5,000 years old, 10,000 years old, etc. Or fingerprinting. Fingerprinting means that I can trace back to the origin of a certain thing. For example, we talk about drinking wine, right? Wine could come from Australia, wine could come from South Africa, wine could come from US. And looking at, because different geometry in the Earth give you different ratio between strontium 86 and strontium 87. So by measuring the ratio between the two isotopes, and then they can fingerprint that, okay, I can determine this wine it comes from Australia, this wine comes from the US, etc. So that's called fingerprinting. I can do isotope dilution. That is, you add an enriched internal standard, and then you measure accurately about your your isotope. So many isotope pollution is for like national NIST, they need to produce a CRM, they need to measure very accurately, they need to do that process. Okay, so now we talk about the feature of that ICP-MS, PQMS, right? So as I said at the beginning, there are 5 components: eco plasma, the CRC cell, the reflex arm, the high definition quad, and also the all 10 digital detector, right? Now I can show you later. You can open up the instrument like open book, so it's called the open book design. And we have a new RF system and also the new web beam system. So why is it called eco plasma? We call it eco plasma because the argon consumption is only half of the amount compared to other ICP on the market. So you save half the argon consumption, right? So you only need up to 9 liters per minute of plasma gas, which is only half compared to other systems on the market. And then you might ask me, oh, you only less gas. Does that mean you're using a mini torch? No, it's not a mini torch, it's just a standard torch. And also you might ask me, oh, you're using such a half amount of argon gas. That means your system is not robust. Well, it's robust. Okay? So, see, we can run with a 9 liters per minute. We can run organics or salt solution, no problem. So just show the robustness. And also we can switch between the so-called hot plasma and cold plasma. Hot plasma means normally we run a hot plasma around 1.3 kilowatt. Cool plasma means that when you want to run some sodium, potassium, calcium, etc. at a very lower power for the better detachment. And then I can show you the next one, right? You watch the next one. So I can switch between the hot and the cold plasma, no problem. Alright, so I'm running hot at the moment. You can see the plasma very bright. And then for a few seconds, I change, you see, it dim down, and that's cool plasma. So at the hot plasma, I was running at 1.4 kilowatt, and the cool plasma, I was already running about 0.75 kilowatt. So if your plasma not robust enough, when you're changing between the different high power to low power, your plasma will not stable, and they will extinguish. But because it's a very robust RF system, so it's okay. Alright, so the next one is about the optics, right? So optic ion beam coming through, it turns 90 degrees into the quadrupole. So we have an ion mirror here. This is called the ion mirror. So when you hear the word mirror, you think it's a mirror we use every morning for makeup. It's not. It basically is a piece of brand stainless steel, and then we apply voltage to control the beam of the ion beam going through. So it is 90 degrees, and then it's the 3D. 3D means that we can control X, Y, Z position to make sure that all the ion beam will going through into the quadrupole. So what it means that we can achieve sensitivity 5 to 10 times higher compared to other systems on the market. And because of these optics. And of course, it is another patent technology. It's another patent technology. Okay, so just simulation, how the iron going through, and then all the rubbish will disappear. Okay, so to remove the interferences, we have an ICRC cell, which is called the integrated collision reaction cell. So it's a very small confined area with very high pressure, and then we inject the either collision gas or reaction gas through, and then because of high pressure, it promote a very, very high collision, and this way we can remove all the interferences. Another patent technology. Okay. So after it go to the quad, after it go out from the con, and then you go to the quad, right, or the quadrupole. So the real quadrupole is a 4-rod, but before it enters the quad, there's a so-called pre-mass filter. So the pre-mass filter is a very curved fringe rod. We call it double axis. Means that if there's any leftover protons, it cannot go past, and then it had to disappear. So it says remove excite neutral. So the background is very low, about less than 1 count per second. And because the background is low, so it gives you very low detect limit. Now there's another term here called abundant sensitivity, right? So what I mean by abundant sensitivity, it means that if I had a very high signal next to a very low signal, if your protocol is not high definition now. High definition, you think about our television at home, right? High definition means that all the pixels, all the image very sharp. And here it means that all the peak is well separated, very well separated. So to define how well the peak can separate, they use a term called abundant sensitivity. So they divide the counts of the high signal one to the small guy, and look at the abundant sensitivity is 2.4 by 10 minus 8. So basically the two bits are very well resolved. Or we call it the protocol is very high definition. Okay, so after that we need to count how many ions, we need to know the sensitivity. So to count the ion, we have a DDEM, discrete dino electron modifier. And then it's 10 order, means that only digital. And then we can give you 10 order magnitude. By how to do it, we just have the filter, the attenuator, the attenuation. So what it means that we can have one measurement and then give you 10 order linear dynamic range. So we don't need to do any cross calibration like other systems. Okay, right. So remember the 5 features of the our system. The first one, it is the something wrong here. So we have the eco plasma, the collision reaction cell, the optics, the high definition protocol, and then the all digital 10 detector, right? So with all this technology, we build the ICP-MS, you can see over there. I'll show you later. Right. So how about to analyze drinking water, right? Drinking water. Okay, so you look at it, we only use 7.5 liters per minute. So only half the argon consumption compared to other systems. And with the parameters we use, you know that remember I showed you about the drinking water guideline before, So for this element between 9 to 40, we don't need any gas, any collision gas. As I say, the interference is only from 80 onward. So from 80 and below, we need to using some interferences gas. So we're using helium or hydrogen, depending on the elements. And then for the high mass, we don't need gases as well. So this is the operating parameters. Then we measure 1643 drinking water and 1640 surface water, right? So the certified value and the measure value, and then the difference recovery, you can see, I don't need to read out one by one, you can see the very well agreement between the measure and the certified value. Okay. All right, so I will go over there and show you about the instruments, okay? So this is the instrument. Remember I said the sample had to be in liquid form. So the liquid sample, you can gather here or you can look up there, doesn't matter. You can gather front, up to you, all right? So this is the sample reduction system here. And this is the plasma system. As you can see, there's a torch. If you want, you can have a closed loop. There's a torch which generates the plasma. And then the sample comes, skimmer comes behind. And then the ion beam will turn 90 degrees into the protocol and then the detector. And of course, you connect to your PC to measure the signal, right? So the sample coming in and mixing with the internal standard. That's why you see there's the TPs here, And then into this is called the nebulizer, concentric micro concentric nebulizer. And then into the back here is a spray chamber, right? The spray chamber is Peltier cool at 3 degrees, Peltier cool. And then the fine aerosol will go into the torch, right? Going to the torch. So to the torch, and then to the plasma. And then after my ionize, and then the ion beam will go to the cones. And then all the interference will be removed by either inject helium or hydrogen. Then turn 90 degrees into the pot, and then measured by the detector, right? So after we measure all the samples, all the calibration standard, right? And then if you wish to do maintenance, the only maintenance you need to do is the cones, right? So easy. If I want to do maintenance, I just pull the lever and then open up. I said open book. It's open book. And then you see the cone here, the sample cone, the schema cone. After you clean, take it out, clean, and then finish, put it back on. After you put it back on, and then you close the door, and then continue running. Of course, you don't need to clean the cone every time. I just show you that that's how you do the maintenance. So it's very simple, easy. So operating ICP-MS is not as difficult as some people might think, right? Although people think ICP-MS is so difficult, so high tech, but it's very simple, easy, as I said. Any questions? Any questions? No questions? No questions, Lorena? No questions. Yeah. Everyone's happy. Everyone knows what to do. Anyone want to buy one too, right?
Okay, ladies and gentlemen, would you please join me to make an applause to our speaker, Miss Tran. Thank you so much.
Yeah, thank you very much. Nice meeting you.
Yep.
All the best for everyone.
Thank you. If you have any questions on plasma quant or drinking water quality monitoring, you can visit Analytik-Jena booth over there.
Yeah, so yeah, you can talk to me anytime. I'm here until tomorrow.
And you have a lot of souvenir for them also, right?
That's right.
Yeah,
you come to the booth.
there.
You come to the booth. You say you're looking for me. I'll give you a souvenir. All right?
Okay, thank you so much, me too.
Yeah.
Okay, ขอบคุณมากค่ะ For the next session, we will talk about the food for your safety and the environment. Okay? Okay. So, ladies and gentlemen, would you please join me to welcome our speakers, Mr. Sompong Vatinchai, the Deputy Managing Director from Design Alternative. Okay, I will leave the stage to you.
โอเคครับ สวัสดีครับ ครับผมพงษ์วาทินชัยนะครับผู้จัดการฝ่ายขายนะครับรองกรรมการผู้จัดการบริษัทดีไซน์อัลเทอร์เนทีฟนะครับครับก็ยินดีอย่างยิ่งนะครับที่ท่านให้เกียรตินะครับมาร่วมฟังนะครับก็จะแนะนำเกี่ยวกับโปรดักต์แล้วก็พูดถึงวิชาการเกี่ยวกับเรื่องของฟูมบูดนะครับ